Okay, let's start. Today, we were supposed to solve the Cooper problem, at least discuss the Cooper problem. This is a problem which tells us essentially how is it that in a superconductor you end up with a formation with pair of electrons. But let me just remind you of the background first. Why do we need Cooper pairs? The answer is simply that superconductivity, at least conventional superconductivity, not high temperature superconductivity, the kind that is explained by the BCS model, essentially is something which can be explained by condensation. That is, you expect a macroscopically large number of the participating particles to be in a single quantum state. Now, this can happen only for bosons, but electrons are fermions. So the electrons which carry the current in superconductivity, they are fermions. So we have a problem here that condensation should not really occur for fermions, they should occur for bosons. Now, as we also said in the last class, bound pairs of electrons, at least for some purposes, behave like bosons. So if we have bound pairs of electrons, that might really show us a way of having condensates out of these pairs, the so-called Cooper pairs. Now, why would there be bound pairs at all? The answer lies in Cooper's theorem, which is what we are going to prove today, which is that another one way of stating that would be the Fermi C is unstable to pair formation if there is an arbitrarily weak attractive interaction. In other words, if you have a filled Fermi C and you consider two electrons just above the Fermi momentum, and they have a weak interaction between them, which is attractive, then they will actually form a bound pair and reduce their energy. So this is actually quite unexpected because of two somewhat different reasons. One is in 3D, weak attraction does not result in a bound state. So I'm just repeating what we talked about the last class. Does not result in a bound state in free space. This is important. If you have a simple attractive potential like a spherical well, it must have a sufficiently large depth before it can admit of bound states. Whereas the Cooper problem tells us that no matter how weak the attraction is, as long as there is an arbitrarily weak attraction, there will be Cooper pair formation. This, of course, is something which is due to the fact that unlike free space, here you have a Fermi C. That is, all states below a momentum kf are completely filled. So this is a very unusual situation, which is not really unusual, but very different situation from free space. This is not unusual, of course, in solid state physics. In solid state physics, electrons, at least at absolute zero, all levels up to the Fermi level are filled. Okay, so this is the first unusual thing, that is, the Fermi C actually somehow conspires to ensure that two electrons which have a very weak attractive interaction will form a bound pair. That is, the energy of the two electron system will become lowered by the attraction. On the other hand, The other unusual thing about this is, of course, where does the interaction come from? In particular, where does the attraction come from? We do expect that the electrons should repel each other. And I already talked about that in the last class. Essentially, what the picture that we have in mind is the following. You are talking of two electrons which are actually quite far apart from each other. In fact, we are going to estimate the size of a Cooper pair today and figure out that they are actually quite far from each other. But when the first electron passes through the lattice of ions, it distorts the lattice ions, it attracts the ions towards itself. And once it passes away and moves to some other part of the solid, the ions, of course, relax back to the original position, but that takes some time. It takes a lot more time for the ions to move back to their positions than for the electron to move far away. Electrons move but more rapidly than the sluggish, heavy ions do. And so, if in that situation another electron comes in that region, it's actually moving in a field which has larger positive charges close to it. The ions, remember, are all positively charged and they have come closer. So the second electron now feels that its energy is lowered because of the attraction with the ions. As an overall effect, what this means is that this electron which was here and has moved far away is actually producing a lowering of the energy of the electron here, of course, via the lattice. So the electron lattice electron interaction effectively becomes an attractive interaction between the electrons, which, if the two electrons are far enough apart, can actually overshadow the repulsion and cause a net attraction between the two. So, any questions about this so far? Because we are now going to go into the mathematical ideas behind Cooper's problem, but this was the physics behind it. So, any questions about this? So if not, let's start using quantum mechanics on the Cooper problem. So of course, when we are doing quantum mechanics, we should definitely start with Schrodinger's equation. So can anybody help me write down the Schrodinger equation for a two electron system here? We just have two electrons, no more, right? Which have some attraction between each other, which is a very small, weak interaction, weak attraction. So what would the Schrodinger equation be for a two electron system? Can anybody tell me what that is? For a two electron system, any two electron system. Yes, somebody help me out here. Tell me what the Schrodinger equation is. Yeah, I think that I'm still connected, although it seems that there is a bit of a problem with some connections. But I hope I am still connected, right? Okay, so can anybody? I think I am. So can anybody tell me what the Schrodinger equation will be for a two electron system? This is, of course, elementary quantum mechanics. What will it be? Yes? Let's make a start. The kinetic energy term will be simply what? Tell me. Of course, you tell me you have to unmute yourself first. So if you're muted, you have to unmute and tell me what this is.
P square by twice m The kinetic energy
Okay,
term.
P square by twice m would be nice, but if I'm using the position space, in fact, we are going to go over to momentum space soon. But if you're using position space, what will the equation look like? Minus h cross square by twice m, then
Correct.
Laplacian with respect to the coordinates of the first particle. Now you have two particles. So you have two terms like this, right? This is Laplacian with respect to x1, y1, z1. This is the Laplacian with respect to x2, y2, z2. Plus weak attractive potential, the Kuba potential, which is some function of R2 minus R1, the separation between the two electrons. This whole thing acting on a wave function which depends on both R1 and R2. This has to be the energy times psi R2 R1, right? This is the time independent Schrodinger equation that we can write down. For the energy, we are going to write it slightly separately. We are going to write it like this. M. Okay, why am I writing it like this? Notice that this thing is actually twice the Fermi energy, right? H cross square kf square by twice m is the Fermi energy epsilon f, which is the energy which an electron at the top of the Fermi sea would have. You have two electrons here. The combined energy just on top of the Fermi sea would have been twice epsilon f, right? Now, what I've done is written the energy of the electron pair not as E, but as some epsilon or small e or whatever you want to call this, plus twice epsilon f. What this means is simply the following, that you are essentially calculating the energy of the pair with respect to the energy the pair would have had at the top of the Fermi sea. So if epsilon is negative, the electron pair has less energy, a lower energy, than it would without the interaction, right? So that is your bound state formation. The fact that the energy of the pair could end up being lower than the energy of the two free electrons right at the top of the Fermi level, that is a sign that by forming the pair, you can lower the energy, and therefore the system would be unstable against formation of pairs. So my aim here is to show that if V is arbitrarily small but is attractive, it is going to lead to the formation of a bound state. That is, it will lead to a solution to this equation with epsilon less than 0. Is this clear? Yes or no?
Yes.
Okay. Now, this is a 2-electron problem, but you definitely know how to handle 2-electron problems. In fact, you have handled 2-body problems before. If you have two bodies which are interacting only with the relative, as a function of the relative distance, R2 minus R1, then it's obvious that a good thing to do would be to introduce relative coordinates and center of mass coordinates. In the case of two electrons, the center of mass coordinates would be simply R2 plus R1 by 2. Of course, it's usually M1 R1 plus M2 R2 by M1 plus M2. But here, both are electrons, so M1 and M2 are both equal. Now, of course, if you were to go over from this set of coordinates, that is R1 and R2, to rho and capital R, the equation would change somewhat. The change would be pretty straightforward. And I'm pretty sure you have all done this before. You'll get two kinetic energy terms again. Of course, the V will become simple. V will be just a function of rho. And on the other side, you will still have epsilon plus twice epsilon F. Psi. Okay, you will have psi, of course, on both sides. So let's. This acting on psi, which I can now think of as a function of rho and r, where rho is the relative coordinate and r is the center of mass coordinate. Now on the other side, we have epsilon plus twice epsilon F, the energy, times psi of rho and r. And V, of course, is a function of rho. The question is what happens to kinetic energy terms. This is something which you should all know. This reducing a two-body system into a one-body problem, effective one-body problem, which you have done in many, many cases, say including the hydrogen atom and other cases. So what will the kinetic energy term become now? It was minus h cross square by twice m Laplacian 1, minus h cross square by twice m Laplacian 2 before. Now, instead of differentiation with respect to x1, y1, z1, x2, y2, z2, we are going to differentiate with respect to components of rho and r. So, the Laplacians which will be involved here will be Laplacian with respect to the center of mass coordinates and Laplacian with respect to the relative coordinates. But there will be two factors here. Can anybody tell me what these two factors will be? The denominator. Will they still be twice m or will they change? Yes?
M will be changed to the center of mass.
So this one, in the first term, this will change to what? It was twice m before. Now what will it become? You're right, but what will it become?
Twice mu, where mu is the reduced mass.
Well, where? Here or here? Or in both?
Uh, in the first term.
No, actually not. That will happen in the second term, in the relative coordinate term. Here, what will happen is twice total mass. After all, even in classical physics, the center of mass behaves like the total mass is there. The total mass here is twice m, right? Because you have two electrons. So this will become h cross square by 4m. Okay? It's actually h cross square by twice m1 plus m2 in general, but here it's 4m. And here it's going to be just h cross square by m because this is where the reduced mass goes. And the reduced mass mu is m by 2 if the two masses are equal. I hope all of you know that, right? So this is the reduction to relative coordinate and center of mass coordinate. Now, why is this such a good thing? Why is this reduction so useful? That is, instead of using R1 and R2, we have gone to rho and R. But what is the advantage of that? Why would anybody want to do that? Yes? What happens to the problem if you get to change your coordinates to rho and R? And you should all know this, right? In fact, you all know this, but maybe you're not finding the right words. The problem essentially, okay, the right mathematical word is the problem becomes separable. And the reason behind that is simple. V rho is only a function of rho. It's not a function of capital R. And what this means is this problem essentially separates to two problems. One is a problem of free particle motion, which is the center of mass motion. And the other is simply a relative motion problem, which is essentially what you focus on when you look at, say, the hydrogen atom problem. Well, the hydrogen atom problem is a two-body problem. You have a proton and you have an electron. But the problem that you actually solve, the so-called Kepler problem, is a reduced problem for the relative coordinate. Because after all, the center of mass will just behave like a free particle. The same here, and solution here can be written down simply in this very simple form. The center of mass, because it's free, it will behave like a free particle and it will have a momentum h cross q, and that will be the wave function for that. And corresponding to that, there would be a corresponding wave function for that particular center of mass momentum. This is something which I have to figure out what this is, but this is the form that you're going to get. Sum over q phi q rho e to the iq dot r. Note that r is there in the wave function, but it's there. Capital R is there in the wave function only in the form e to the iq dot r, because ultimately this is a free particle and it's going to behave like a free particle solution. In addition to this, there's actually also an additional piece which is of no interest right now, which will be useful later on, which is the spin part. We are not interested in the spin part right now, basically because our Hamiltonian does not have spin. So to solve for this problem, we will not need to worry about the spin part. So for the time being, I'm not going to write down the spin part. So I will just ignore that. Okay. Any questions so far? But then what I'm going to do is something a bit special. I'm going to say that only those Cooper pairs will be very useful for our system, which are essentially at rest with respect to the solid. That is, which are essentially such that the center of mass momentum is zero. We will see why later, but for the timing, let's focus on that. We will only look at center of momentum zero particles. There's total momentum zero pair of particles, which means Q will be zero for the particles of interest. And instead of a sum over all Q, you just have one term. I should have called this phi zero of rho, but I will just, since there's only one value, I'm going to drop the index, call this phi of rho. So this is the kind of function that I'm going to look at. Phi of rho, no R dependence whatsoever. This is the zero momentum case. Okay. If you want to look at what happens, if you have a momentum, then you can solve the full problem. It's simply not necessary for us right now. Anyway, the problem, even with other values of the center of mass momentum, is not really that difficult to solve. But we are interested only in this case, where the center of mass is relatively stationary with respect to the solid system. So we are looking for solutions to this equation of the form some function of rho, right? And that means this quantity, which involves Laplacian with respect to coordinates of r, differentiations with respect to r components, will simply give you zero. And you are going to live with minus h cross square by m Laplacian. Now I'm dropping the rho for the time being. Oh, okay, let's keep on writing the rho. Anyway, no harm. Phi of rho. So this is a much simpler problem. But even now, depending on the v of rho, it may become a simple or a difficult problem. Now, what we are going to do is we are going to investigate this problem in momentum space. There's a reason for that, and the reason will be clear very soon. But after all, momentum space is a legitimate thing to look at. In fact, when you started by saying, one of you started by saying that the Hamiltonian is P1 square by twice M1, etc., etc. That was, of course, a momentum space version of this. So in momentum space, phi of rho can be written down in this form. And now, one of the reasons why momentum space is so nice is that the action of the Laplacian on this is very, very simple. Can anybody tell me what this minus h cross square by m Laplacian rho phi rho will become? Once you replace the phi rho by this, what will this term become now? Now, the Laplacian rho involves differentiation with respect to the components of rho vector, and k is an independent quantity. As far as that is, as far as these differentials are concerned, k is a constant. So, first of all, this is a sum. The Laplacian can move into the sum, right? That is, instead of calculating the Laplacian of the sum, I can do the Laplacian first and then do the sum. And the gk's are constants as far as Laplacian rho is concerned. So Laplacian essentially goes and acts on this term. So what is the Laplacian when it acts on this? Anybody? You must have done this several times before in many, many different places. In quantum mechanics, definitely, also in electromagnetism, in many other places. When you calculate the Laplacian of e to the I k dot r, here we are using rho, but it's the same calculation. E to the I k dot r, if you take the Laplacian of that, what do you get? Yes?
minus k square e to the power I k rho.
Exactly. Every time you differentiate with respect to component, the corresponding component of k comes down with an extra I. So two derivatives, you get my I square into kx square plus ky square plus kz square. So this becomes h cross square k square by m. M and not 2m simply because this is a reduced mass problem. Sum over, this is actually inside the sum over k, g of k with the ik dot. So in terms of the momentum wave function g of k, my Schrodinger equation essentially ends up becoming this. Sum over k, h cross square k square by m, g of k to the ik dot rho, plus sum over k, v rho, g of k to the ik dot rho. This is simply v into phi. On the other side, you have sum over k. Rho into, of course, epsilon plus twice epsilon f. So now what I want to do is, from this sum, I want to extract the value of g of k. Any idea how this, for example, from this, which is essentially g of k to the ik dot rho summed over all k, this is an overall constant. From this, how can I get g of k out of this? This, of course, is a wave function written in terms of momentum components. In other words, is a wave function written in terms of the Fourier components. And what I want is an individual Fourier component out of it. So how will I get g of k out of the sum? Any idea? How can I get g of k? So from this sum, which I can of course also write k. Okay, let's say I will write this with k prime. I can do that. The dummy index, right? I can change it to anything I want. From this sum, g of k prime e to the I k dot k prime dot rho, I want to somehow get g of k. One individual term. How does one get that? This is a Fourier transform, basically, a discrete Fourier transform, but a Fourier transform nonetheless. And from that, I want to get one component out. How do I do that? Again, this is something which I've done in many, many different places, over and over again. Okay, hint. If I were to integrate this thing, over the entire lattice, what will I get? Yes?
Delta
Okay, let's
K
start
prime.
delta kpk prime. Well, almost. Actually, if k prime and k are not equal, but these are, of course, those, if you're putting this whole system in a box of side L, then k and k prime can only take the values allowed by the periodic boundary conditions on L. And when you use that and you do this integration, you will find that from the periodic boundary conditions, you will get exactly 0 whenever k and k prime are not equal. But when k and k prime are equal, well, what will you get? What are you integrating when k and k prime are equal? How much is this quantity? When k is equal to k prime, how much is this exponential?
So 1.
1. So you're integrating d cube rho. Okay. So what is the integral of this volume? It's nothing but the volume of the solid, right? So I should not get delta kk prime. I should get volume of the solid into delta kk prime. But the volume, well, I will not call that V simply because I'm using V for the potential. Let's call that LQ. Okay. Now, in order to make use of this, what I will do is I will multiply both sides of this equation with e to the minus I k dot rho. And that's precisely why I changed the summation index to k prime before, because I don't want to confuse this k prime with this, which is a summation index, with this k, which is a definite k. I want to multiply it throughout everywhere. And then I want to integrate the whole thing with respect to rho. Okay. And simply make use of this condition. So that's easiest to do here. Note one thing, that I am integrating over rho. As far as that integral is concerned, k and k prime are constants. Only rho is a variable. So this integral will go inside the sum. As we always assume that integrals and sums can be interchanged. And then the integral will also go right through the g of k prime, because these are constants. And you're just going to end up integrating into the I k prime dot rho minus into e to the minus I k dot rho. Right? So this side, the right hand side, because of this delta function, will simply give you L cube sum over k prime g k prime delta k k prime epsilon plus twice epsilon s. Is that okay with everybody? What about the left hand side? What will happen with this? This will give you k prime right? Okay, plus one more term which comes from this one. So these two terms can become very, very simple. Right? Because the delta k prime makes this summation simple. This becomes h cross square k square by m. K prime becomes k, g of k, plus, of course, this term is still to be written, into L cube, of course. On this side, you have L cube, g of k, into epsilon plus twice epsilon s. So these two terms, the kinetic energy term on the left and the energy term on the right, they become very simple in momentum space, as is to be expected. Now, what about the other one? Here, the same advantage does not really occur because you are no longer, here you are not really integrating just into the I k prime minus k dot rho with respect to rho, because you also have v of rho in the integrand. So what you're doing there, you have to actually calculate this integral, which of course depends on the nature of v of rho. So you cannot really say how much this is going to be without knowing what the attractive potential is like. But okay, what will this quantity depend upon? Sum of k prime, gk prime is still there. Gk prime will come out of the integral because it's constant. V rho will stay inside. So what will this quantity depend upon? This whole thing? Yes? I'm not asking any specific question about the superconductor or anything. I'm just saying if you did an integral like this where v was some function of rho, then what will the final integral depend upon? Will it depend upon rho? The integral, the final result? Yes? Will the final result depend upon rho? Or you actually no. Once again, I am now worried about whether I am connected. Am I?
Yes.
So this is a very trivial question. Has nothing to do with quantum mechanics or anything. It's just basic maths. If I do an integral of this kind, what will it depend upon? What will the result depend upon? In particular, if you're integrating something with respect to x, can the result depend on x? By the way, all these integrals are definite integrals. There's no such thing as indefinite integral really in the whole game. This is being integrated over the entire volume. So this, okay, let me give you the answer, but I think all of you know this. The answer is that this result cannot depend upon rho. The only thing it can depend upon are k and k prime. Of course, it depends on any parameters which are there in the definition of the V, but the result depends only on k and k prime. And just, well, I could have written this as V tilde kk prime, but from the fact that I'm using two k indices, it should be obvious that this is the momentum space representation of the potential. Instead of V of rho, you now have V kk prime. And I've thrown in the extra L cube just because that will help us in writing the rest of the equation neatly. I can cancel the L cube for all the three terms. So what we have done is we have rewritten the equation, the Schrodinger equation, in momentum space, in terms of the momentum wave function g of k, in this form. Okay. By the way, so far whatever we have done is elementary quantum mechanics. Maybe the only non-elementary thing about this is that we are actually working in a momentum space and not in position space, the one which we are usually used to. But this would be true for any two particle system, not necessarily the Cooper problem, right? In any two particle system, if you were to go over to momentum space, the equation would end up looking like this. And this is a very general equation. It's called the Bethe-Goldstone equation. This equation will be valid in any two electron system, not necessarily the Cooper problem. But what makes this specifically the Cooper problem is the following. And this is where going over to the momentum space really makes a huge amount of sense, which is this. What can you say about G of K? In the Cooper problem, there's something about the G of K in the Cooper problem which can be stated by the very assumption that there is a filled Fermi C. It will simply be that if magnitude of K is less than Kf, the free energy, the Fermi energy, then G of K will have to be 0. This is the Pauli exclusion principle at work. All we are saying is that because all momenta levels below the Fermi level are completely filled, at least we are assuming that we are very close to absolute zero, which we are in the case of the kind of superconductors we are talking about. And there are no available energy levels or available, all the wave functions below are already filled up. So any G of K with magnitude of K less than Kf will not be available for my pair of electrons. Okay? Because these levels are already filled up with electrons. That's where the filled Fermi C comes in. Okay? And this is the sign of the electrons being fermionic. That if you already have an electron sitting in an energy level, another electron will not share that particular wave function. Okay? Now, even so, that means that in the general Bethe-Goldstone equation, this sum over K prime could run over all possible momenta. Here, this actually runs over momenta which are only larger than Kf in size. All momenta smaller than Kf will not participate in this sum. Okay? Clear? But even
Yes.
with that restriction, yeah. Any questions about this? That's all. No? Even with such a huge assumption that is made in the Cooper problem, the problem is still very, very difficult to solve for an arbitrary VKK prime. That is for an arbitrary V of rho. So what Cooper did was actually work with a model potential, the Cooper potential, where he made the following physics-based assumption that basically what he was saying is if an electron moves too fast, so fast that the oscillations of the lattice simply cannot keep up with it. If either the electron which has moved through the lattice originally or the electron which is going to follow up, the second electron, if either of the electrons are moving too fast, then what will happen is the ions will not respond at all and there will be no effect. So there will be no attractive effect between two electrons and VK prime will be 0 if the following happens. If H cross square K square by twice m, which is the kinetic energy of one of the electrons, minus the Fermi energy, so how fast it's moving with respect to the Fermi energy, if that is less than epsilon f, sorry, less than the characteristic energy of oscillations of the ions. So if the electron's energy is much, much higher than the characteristic energy which the um, ions can respond at, which is typically given by the Debye energy, right? The rate at which the ions can oscillate is essentially characterized by the Debye frequency, and h cross times that is the Debye energy. So if this happens, sorry, I got the sign wrong. If this happens, or if this happens, if either of the two is too big, then what happens? The Either the first electron moves through so fast that the ions don't get time to move and the lattice doesn't get distorted, or the second electron moves so fast that it even in the with the distorted ions it hardly feels anything. Okay, so this is a physically reasonable assumption to make. So this was basically the kind of potential. This is based on the mechanism producing the potential in the first place. Yeah. This attraction was caused by the electrons distorting the lattice and the distorted lattice acting on the electrons. If the electrons have too much energy, either the first one or the second one, then there will be almost no attraction. So Cooper said, okay, let's assume that in that case it's going to be zero. Otherwise, which of course
Sir,
means that both, yeah, go ahead.
sir, these two conditions that are written in OR is for the two
Hmm.
electrons, right?
Right, right.
Okay, sir.
So both the electrons, if any one of the electrons, that is, if either of there are two electrons which are interacting here, and they have the momenta k and k prime. If any one of the electrons have too much of an energy, any one of the two, then there will be no interaction. Otherwise that means that h cross square k square by twice m minus epsilon f, sorry, minus epsilon f is less than h cross omega d, h cross square k prime square by twice m minus epsilon f, even that also is less than h cross omega d. And of course, the connection here is and. If this doesn't happen, that means both of these have energies less than the limits prescribed here. And there, of course, here that there will be an interaction. The interaction will be very complicated. But Cooper just took a simple model. Just said, okay, let's say it's just minus V0. Okay? Clear? So he had a physics-based idea here that if the electrons move too fast, then the lattice will not be able to respond and hence there will be no attraction between the electrons. So this is physically reasonable. If on the other hand the electrons don't move too fast, then there will be a radiation, of course. But then of course you would expect that the potential strength will actually change if you change k or k prime. But now what Kuba was saying is the following. This is again not just basic physics. It's also some idea about the numbers involved. The typical Debye energy h cross omega d and the typical Fermi energy of an electronic system. You need to have an idea about how big they are. You should already know that because you have actually worked a lot in in condensed matter physics. The Fermi energy and the Debye energy are both very useful quantities there. But let me just give you the answer here. The Fermi energy is huge compared to h cross omega d. So what we are really saying is the electron energy, if this is kf, I'm actually trying to draw a spherical shell, but in two dimensions this just looks like a circle. So this electrons here will have energy epsilon f. If the electron's energy is slightly bigger, is within plus minus h cross omega d of that, what you're really saying is there is a inner shell and an outer shell, some minimum value of the momentum and a largest value of the momentum for which this will work, for which there will be a interaction. Unlike my picture, the way I've drawn the picture, what is important is that this gap, which is twice h cross omega d, is actually very, very small compared to the Fermi energy. So this is a very, very thin layer. Okay? Yeah. So only electrons within this very thin, narrow layer interact. And because this is so thin, although you would expect a variation with a K, because the change in K is so small inside this very thin region, but assume that you can replace the potential by a constant. Is that okay? So what is an important physics ingredient going on into this is h cross omega d is typically much, much smaller than epsilon s. Around 100 times smaller in most systems, if not more. Okay. So you have a very narrow region, narrow band within which the electrons have to be, they have to interact. And within the narrow band, the variation with K can be ignored because the band is so narrow. Is that okay? So this is a model which is based partly on the physics, partly because it will make life simpler because of this assumption. But even this assumption is not too bad. Okay. Any questions about this? Because this is the critical assumption in the whole thing. The rest was pretty straightforward, standard quantum mechanics. Yes. Questions? Now, let me just write this just below this. You take the Bethe-Goldstone equation, which is valid for all two electron systems, and then put in the Cooper condition. Then what happens? You just move. Or rather, let's move it the other way. Let's write minus epsilon. G of Vk k prime, remember we assume is minus V0 within a narrow region, is fixed there. Outside it is 0. So V0 Gk k prime. Sum over k prime. But there's an important restriction. This sum is not over all k prime. This sum is over only that narrow region of k prime, which is allowed by the conditions. Right? Got it? Yes? Is that okay?
Sir, can you repeat it once?
So all we are saying is this is the Bethe-Salzgitter equation, which is valid for all systems. So here I can, of course, move this side, which also is gk into something, to the other side. So that's what we have done. I've taken this to the other side, so it should be minus gk prime vkk prime summed over all k prime. Okay? But what we are saying is, according to Cooper's model, so far, if I just written this as minus g k prime vkk prime summed over k prime, and all k prime, if I had just written this, then I would have just done a simple bit of algebra on Bethe-Goldstone, just change sides. But now I'm saying that vk prime, the condition that we have assumed is it's minus v0, a constant independent of k and k prime, within this narrow region where this condition holds. Outside it's 0, which means that where this condition holds is just minus v0, so I can pull it outside and write this as plus v0. plus because there's already a minus sign outside. Okay, but because the gk prime actually vanishes everywhere outside that narrow region, the sum over gk prime is really not over all possible k prime. It's only in that small narrow region, right? Where this condition holds. And if for k prime, this condition holds. Okay? And for k, this holds. Right? Is that okay? Now we have to solve this equation. We basically, what do we really want out of all this? That's important to keep track of. What we want out of all this is, of course, a solution to the Schrodinger equation, which means we want to know these quantities. We want to know g of k, that is, what is the momentum wave function. We also want to know what is the energy, both of them. Okay. So this will give me the wave function, and epsilon, after all, is very important because if I find out the epsilon and find that it's negative, it means that I have shown that the bound pairs can be formed. Now, this is where the fun part is. How do you actually get the epsilon out of this? Yes? Okay, just a hint. You can also rewrite this equation rather trivially in this form. G of k is V0 sum over k prime g of k prime by this is a trivial statement, right? I've just written this by dividing. But this should give you a hint as to ensure a way of getting rid of gk from both sides. After all, you have two unknowns here. What is the wave function like? Also, what the energy is like. If you get rid of one of them, that will give you the other. If you want the energy, you should get rid of g of k from the equation. Then the energy should come out of the equation. Is that okay? So how can you get rid of g of k? And the answer is childishly simple, actually. And anybody give a suggestion? How do I get rid of g of k from both sides of the equation? Eliminate that. How do I do that? Actually, it's very, very simple. Let's say the left-hand side, of course, depends only on k, right? So one thing you could do is sum up both sides over k. Sorry, over k. Here is both sides are over k and the sum has a prime to remind you that you're not adding up over all k, you're only adding up over those k's which are allowed by this non-zero v condition. That is, with this condition. Now, the right hand side is, of course, just a sum. What about the, sorry, left hand side? What about the right hand side? There, the constants can move out of the sum. Which things here are constants, independent of k? On the right hand side, what are independent of k so that I can move them out of the sum over k? Sorry, this is again a sum over k. Sum has a prime to realize that, to remind you that not all k values are being summed up. So V naught is a constant and we can go out, right? Anything else that you can see is a constant which can go out on sum?
gk prime.
Which one?
If yeah.
Sorry, you're breaking out. I mean, I am hoping that my voice sounds better than your voice sounds to me. because I can't really hear what you're saying. I just hope you can hear my voice better. This sum on the top, does it depend on K prime or K?
K prime.
No, actually it doesn't. It doesn't depend on either K prime or K. It does not depend on K prime because K prime is being added up, right? Once you add up over something, it no longer depends on that variable. This K prime is just a dummy variable of summation. And that's important because note that first of all, it does not depend on K, so it can come out of the sum. And also, this sum on this side, which is a sum over K of GK over this restricted region, and this is a sum of GK prime over K prime over the same restricted region, are exactly the same, right? Because K prime is a dummy index. It does not depend on whether you call it K prime or whether you call it K. As long as you add up over all the same momenta, you are going to get the same result. So you end up with this very, very important equation where G actually gets lost. Where you no longer have the G, which means this becomes an equation only for epsilon. Got it? Is it okay? Yes? Sorry, I can't really make out whether you're trying to say something.
Yes, sir.
Okay. So now, how do you solve this problem? Okay, we have already solved the problem actually. But I need an expression for epsilon to finish off the calculation and show that epsilon is negative. So what I will do is I will do what we do all the time. After all, this is sum over K. The Ks are for a large system, for a macroscopically large system, which the superconductor is, all the allowed momentum values are very close to each other. So you should be able to change this into an integral. And what we will do, this quantity, which is essentially the energy of the electron with respect to the Fermi level, we are going to call that psi. It is just change of notation. So denominator here simply becomes xi minus, twice xi minus epsilon, right? H cross square k square by twice m is the energy of one electron. We're subtracting from that epsilon f. One free electron's energy is here. With respect to the Fermi level, you call that psi. So this is twice xi minus epsilon denominator. In the numerator, what you need is basically the number of allowed states between xi and xi plus d xi, and you need to integrate that. So this is the density of states. This again should be very familiar. Everywhere in condensed matter, you have sum over Ks, which you change into a volume, into an integral over d cube K, and then you change into an integral over energy by invoking the density of states. But what is very important is what kind of integration are we going to do, from where to where? So this is the xi, right? H cross by k square by twice m minus epsilon f. What is the smallest value I can, the lower limit for xi? What should that be? Remember, g of k vanishes whenever mod k is less than kf. The smallest value for hk square is given by h cross by k square by twice m equals epsilon f, right? G of k is 0 for mod k less than kf. This is the filled Fermi C condition, which means this integral, the lower limit of this is one, the smallest value of k that will participate here is h cross square k square by twice m equals epsilon f, right? And what about the highest value? Note that if the h cross square k square by twice m exceeds epsilon f by more than h cross omega d, then v vanishes. Then you're not going to include that in the sum. The restricted sum is basically because if you go too high up in energy, there is no interaction. So this integration is from 0 to h cross omega d. Okay. But now comes the important thing. Xi basically is the energy of the electron relative to the Fermi level. So it goes from 0 to h cross omega d. But the Fermi energy itself is much, much bigger than h cross omega d, which means that Xi changes over a very narrow region from 0 to h cross omega d, whereas, or other words, the energy of the electron changes from epsilon f to epsilon f plus h cross omega d. Whereas that's a very small, narrow region, right? Compared to epsilon f. So what we will do is we will make another approximation, which is a very reasonable approximation, which is this density of states will be replaced, which is a function of Xi, of course, will be replaced by its value at the Fermi level, value at 0. All I'm saying is when energy changes from epsilon f to epsilon f plus h cross omega d, the density of state hardly changes. So it stays whatever its value at the Fermi level is. So okay, now we are done actually, essentially, because now we have this problem in such a form that I can easily integrate this. Remember, the left hand side is 1 here. So this is V0. N0. N0 is the density of states at the Fermi level. By the way, that quantity is actually very important in many physical situations involving any system which has a Fermi level. The density of states at the Fermi level, which is the quantity sitting here. And the integral is trivial, right? It's just log of 2 xi minus epsilon at 0 and h cross omega d. So V0 omega d minus epsilon by minus epsilon. So this is the equation. This is equal to 1. Or sorry. So now can you tell me one thing? From this equation, can you tell me what the sign of epsilon will be? On the left hand side, you have an exponential, right? Exponential of a quantity which is positive or negative. Yes? This 2 by V0 N0. N0 is the density of states at the Fermi level that has to be positive. What about V0? Is V0 positive or negative?
For attractive case, V0 is negative.
Well, actually, you are almost correct, except for the fact that you should remember that we wrote the potential. Sorry, I've just moved that out of the screen completely. But if I can, I'm not sure whether I can recover that. But the Cooper potential that we wrote has the form V equal to minus V0 or 0, right? You're right that for an attractive case, the potential should be negative. But V0 is not the potential, it's negative V0 is the value of the potential component, right? VKK prime, we wrote as minus V0, which means precisely because we are talking of attractive potential, V0 should be positive. Is that clear? When I wrote that as minus V0, I'm assuming that V0 is positive. That's why VKK prime, the momentum matrix element of the potential, that's negative. Clear? Is that okay?
Yes, sir.
So now can you tell me what can you say about this right hand side from the fact that V0 and M0 are both positive? Yes? Come on, this is a positive number. What do you know about the exponential of a positive number? Is it positive or negative, first of all? Is an exponential of a positive number positive or negative? E to the power something, is it positive or negative? That's what I'm asking. Or when is it positive, when is it negative?
Positive.
Yeah, it's positive. And it's positive for all values of x, right?
Yes.
True. It is all real values of x. But the question that I have for you here is the following. If x is positive, what can you say about e to the power x? More than that, it's actually e to the x is positive no matter whether you take negative x or positive x. Or for positive x, what can you say about it? First of all, e to the x is an increasing function of x, right? If you increase x, it increases. What is the value of e to the x at x equal to 0? In other words, what is e to the 0?
1.
It's obviously 1, right? But e to the x is an increasing function of x. So for positive x, what can you say about its value? What can you say about the value of e to the x given the fact that it's an increasing function and at x equal to 0 is 1?
It will be more than 1.
Exactly, it will be more than 1. But it's 1 minus twice h cross omega d by epsilon. How can it be more than 1? How can this quantity, which is 1 minus twice h cross omega d by epsilon, be more than 1? And the answer is very
Epsilon
simple.
is negative.
The only way this can be more than 1 is epsilon has to be negative. Right? Which
Yes.
actually tells you that there is a bound state. The energy of the two electron system in the presence of this weak attractive potential is actually less than the individual, than the energy it would have had if there had been no interaction. Clear? So this is where we have managed to prove Cooper's theorem. The energy actually is smaller if this there is a level, energy level for which the energy is less than the individual energies of the two electrons. And that's why you have a bound state. And by the way, you expect the energy to be very small in size, which means that twice h cross omega d by epsilon, or rather minus twice h cross omega d by epsilon, would actually be much, much bigger than 1. Right? Because epsilon is typically very, very small. It's very weakly bound. And that means that this formula really tells you that twice h cross omega d by epsilon is minus exponential 2 by v0 and 0. And therefore, the bound state energy, there's a minus sign in the bound state energy, which shows that it's a negative quantity. This is an approximation, of course. Uh, the actual formula is slightly more complicated, but twice h cos omega d by epsilon is so much bigger in size typically than 1 that this is a pretty good assumption. Okay. So here, very, very weakly bound state of the two electrons. And one, okay, I will just end today's class. I wanted to actually calculate the size of the Cooper pair also today because that's going to be useful for estimating various physical things. But we are going to talk about that in the next class. But I would like to point out one thing. This is a situation where we are talking of a potential V0 or strength is V0, and that gives rise to an energy, bound energy. Now, when V0 goes to 0, epsilon goes to how much? What's the limit? That's pretty easy to see, right? When V0 goes to 0, this thing becomes infinitely large, so you have exponential of minus infinity, which is epsilon goes to 0. That's as expected. If the potential vanishes, there is no binding energy. However, in a typical perturbation problem, the energy of a system that typically depends on a power series of the potential, right? When you do perturbation and solve a problem, that's a typical method that you use. Get first order corrections, second order corrections, and so on. And these corrections depend on the strength of the potential. They are actually proportional to various powers of the potential. Is that right? The first order correction is proportional to the potential. The second order correction will be proportional to the potential squared, and so on. But note that if you were to take this formula, what you actually get and expand out the exponential, you don't get powers, right? You get negative powers. And in fact, you get all negative powers. This is a sign that perturbation theory will never give you this result. This is a non-perturbative result, which perturbation theory cannot give you. Okay? Clear? So this perturbation theory is a technique that we use all the time when we talk about weak potentials. But the fact that the Cooper problem, in a Cooper problem, you have a bound state, is something which perturbation theory would simply miss. It would never have given you this result. This is something which we can get because we can, at least within this approximation, we can exactly solve the problem. With it, okay, that's a bit of a bit of a funny thing to say. But once we have made the approximations that are there in the Cooper problem, the resulting problem is exactly solvable. And that exact solution gives us a binding energy, which perturbation theory would never have given. You can easily see that from the very form of that expression. This is an inherent non-perturbative result. A perturbative result is typically a power series in the strength of the potential. This actually has an essential singularity as V0 goes to 0. Right? Because if you expand this out in powers of V0, you get negative powers and you get all negative powers. Yeah. So this is basically Cooper's solution that you will get a bound state. But what will the characteristics of the bound state be like? For that, we need to know the wave function. But that is not really a problem because once I know what the energy is, once I know what the energy is, G of k is simply V0 into this quantity, which is a constant, divided by this quantity, which is already known. So next day, we are going to begin by using this wave function G of k to figure out what the size of a typical Cooper pair is. And the answer will be quite surprising. How big or what is the kind of separation between the two electrons in a Cooper pair have? The answer may turn out to be pretty surprising unless you know it already. And then try to see how you would incorporate this idea about Cooper pair formation and try to see how we can get a system which explains superconductive phenomena for you. So that will be the next class. That will be next Tuesday at 7. Okay. So next Tuesday and Friday we will meet again, and I'm not very sure whether I can finish it off in 2 classes. If I can't, then I will need 1 more class. I'll try to finish it in 2 classes. Let's see.